We would choose, very likely, if the spacecraft was healthy, to perform a TCM if we were just a handful of kilometers off of where we thought we were. Because we want to stack the deck in her favor and sort of put her right down the middle so she doesn't have all that much to do when she gets to Mars.
And when would that decision be made, tomorrow or today, about whether to do the burn or not?
There's an opportunity to talk. We'll tomorrow, about middle of the day, we'll start making that decision.
Okay. And you really piqued my curiosity when you said that this landing system was the least crazy of the options that were on the table. Could you maybe pick one or two other scenarios that were not immediately laughed out of the room, and where you what were kind of the trade-offs that led you to this system? Thanks.
Certainly. The leading two, the runners-up were maybe don't look that crazy to the layperson, but their performance and their risks throw them into the crazy category. Though they are legged landers, like we've successfully put on the surface of Mars in Viking 1, 2, and the Phoenix lander. Also the Apollo landing system. They are not very stable. And when you stick a rover of the size of Curiosity on the deck of a legged lander, it becomes very unstable, and you need to land on a flat top spot to be able to make that happen. So that's where that one loses. And the other one was the airbag system that we've successfully used during Pathfinder and the MER's Spirit and Opportunity. Unfortunately, we don't have fabric here on Earth strong enough to build airbags that would work for a rover the size of Curiosity. And so the bags would shred, not giving Curiosity any protection, and that's what throws that one out.
Okay, we've got a question. Was that a hand I saw right next to Irene? Yes.
I read somewhere that one of the concerns about not landing the rover with the descent stage was that it would kick up so much dust it would foul up the equipment on the rover too. Was that a concern, or was that already outweighed by the fact that it would be unstable?
The issue of dust is certainly one. The issue of the interaction between the plumes and the surface is a very important issue. Dust is one of those. But actually, when you get a propulsion system close to the surface, you develop quite a bit of pressure that can make that landing terrain interaction very unstable. And so the way legged landers have approached that in the past is they come in very quickly, so that the guidance system doesn't have a chance to try and control it. It's more of it looks like a soft landing, but really it's a controlled impact that has features that exacerbates the instability. And it also means that the computer has to look for a very quick signal of touchdown. And as some of you may know, one of the leading candidates for the reason we lost the Mars Polar Lander was it triggering off of a touchdown sensor some 80 meters above the surface and turning off its rockets and crashing to the surface. So in general, we don't like that technique either. So there's several reasons to keep the descent stage away from the ground, the first of which being remove that pressure and that instability, and then the dust is certainly a good thing to keep off the vehicle to the degree that we can.
Okay, and a reminder that if you do have a question, please raise your hand so we can get the mic to you, and also state your name and affiliation. Let's go to the back row right there. Conan.
Adam, much has been said on the Internet about NASA's 7 minutes of terror. And this is obviously very sophisticated procedure that you're going through. Is there any particular minute of those 7 minutes that you are most focused on and most worried about?
Like any good parent, I love each of those minutes equally. In different ways, of course. They're all different minutes. Certainly the novelty of the guided entry, and especially the novelty of the sky crane maneuver at the end, draw a lot of the attention of the team's anxiety. There's also that parachute that we use. It ends up being parachutes are fundamentally sketchy kinds of devices, right? The U.S. military troops jump out of airplanes all the time, and we've done amazing research about how to have them jump out of airplanes safely. But when they do, they take a second parachute. Because with all that work and all that control, there's still enough uncertainty when you use a parachute that you would like to have a backup. Well, it ends up being you can't work a backup in this system. And so we have sort of a fundamental device reliability limit. We've done everything you can do humanly possible to improve our odds with that parachute, but that's sort of a fundamental, irreducible risk about making it to the surface of Mars, is you got to use a parachute. So maybe sky crane, guided entry, parachute are 3 minutes of those 7 minutes that maybe take an extra bit of attention.
Okay, do we have more questions? Yeah, let's go to the third row right here in the maroon shirt. Craig?
Yeah, hi, it's Craig Cavalt with America Space and Aerospace America. Adam, and anyone else chime in too. Given lift and guided entry, would it be a correct analogy that you can relate this all the way back to Orville and Wilbur Wright's genius of first developing and measuring lift and control in the history of flight, taking it to Mars now?
Interesting question. I'm drawn towards nerding out with that question, so excuse me for doing that. The only thing that makes it tough for me to go there is that Orville and Wilbur were using Bernoulli lift from and we use a negative lifting body, or that is to say, we use blunt body momentum associated lift as opposed to Bernoulli lift. So whereas Orville and Wilbur fly forward and get lifted up, we sort of come crashing forward, pitch our nose down, and develop lift. You know, the Wright brothers, you pitch the vehicle up, it gets more lift. For ours, we get lift by pitching down. So aside from that, which sort of stymies me a bit, certainly it is use of lift. And we aren't the first. You know, we're using repurposed Apollo guidance algorithms that were used in the 60s and 70s. And we're using them novelly in an autonomous mission at another planet. It's also true that Viking used lift. It just didn't guide the lift. It used lift to improve its performance at Mars. So we're taking pieces of history, perhaps reaching all the way back down to the Wright brothers, and we're using those in a novel application for us. Yes.
Okay, let's get the mic to John Johnson right there. And please go ahead and,
Since you nerded out on that last one, do you mind nerding out on the tungsten weights to explain that a little bit better, how it guides itself that way?
Certainly. Symmetric aeroshell, symmetric body, if the center of gravity, and shaped such that it's statically stable aerodynamically. So that is to say, if the center of mass were right in the center of the body, and it was coming in like this, it would have zero angle of attack. We put 168 kilograms of tungsten in 6 slugs of 168 divided by 6, whatever that number is, about 30, here. And that moves the CG, the center of gravity, and so the vehicle tilts a bit. Its static equilibrium point, its aerodynamic equilibrium point is an angle of attack. That angle of attack means that there's a differential pressure across the bottom. That differential pressure results in a lift. I'm feeling I'm over-nerding.
All right, we've got time for a few more questions if anybody has any here at JPL. Has everyone had a chance to ask a first question? If so, we'll go back to Irene Klotz over there.
Thanks. I was just curious if there was any thought given to, instead of using just a dead weight, to actually putting something that might be scientifically or educationally useful instead of that tungsten.
Well, I know 160 kilograms of tungsten who think that they're doing just a dandy job. Thank you very much. Certainly, we have speculated and thought of different ways of doing it. It feels... some folks think it's a tad wasteful to be hucking off this inert mass. Inert mass ends up being some of the least expensive mass to put on Mars. You know, chunks of tungsten, as opposed to kilograms of engineered or other, complex pieces. We studied and traded many different methods of developing that lift, including moving mercury around inside the heat shield, having aerodynamic fixtures on the other side to develop lift. And this was the simplest, most reliable, and most cost-effective method for us to get the job done.
If you're asking the question as to whether or not you could have put something meaningful in that spot, the problem is once you eject it, you've got to land it itself land safely, and then you've got the communication issue of how does it talk back to us, and those are all very, very difficult engineering problems that really are not the main focus of the mission, and so those things tend to get avoided in that kind of a discussion.
Thanks. And Doug, could you just address the significance of this success of this mission with regards to the planning ongoing for what's going to be coming down the pike?
Sure. Well, there's an engineering impact and there's a scientific impact. The engineering impact is the ability to get a metric ton to the surface. The studies we've done over the years and that the current planning team is doing, really we haven't come up with missions in the robotic science community that really need more than this kind of a mass delivery to the surface. So I think what we have is a workhorse for the future. And that's been developed from starting with Pathfinder, working through the MER missions, and that includes software advancements that we've made for navigation, auto navigation, things like that. So that's one important feature of this. The ability to rove longer distances, longer lifetimes on the surface, more advanced instrumentation, et cetera, all play into that. Scientifically, the Mars Science Laboratory and the Curiosity rover itself specifically, it's a transition mission from follow the water of the last decade to seeking the signs of life and heading towards sample return, which is what the Decadal National Academies of Sciences Decadal Survey recommended as the next major step in the exploration of Mars and the exploration of the solar system. This mission, including, so scientifically, it bridges that gap with habitability analyses. Back to the engineering, it also helps us bridge that gap as well. With a one-ton capability to the surface, we can actually implement those types of missions as we move forward. So all of these things really feed the advanced planning team that's working now to come up with options and approaches for the next decade. So all of these things will get factored in.
Okay. Oh, we have a question over here, fourth row back in the orange or coral sweater.
Hi, I'm Elizabeth Landau with CNN. I was just wondering, this is also for Doug, if there have been specific engineering improvements so that this rover won't get stuck the way that Spirit did?
That's really better for Pete to answer. Sorry, Pete, but
That's okay. Well, trafficability, what we call trafficability, which is this problem, is a subject of a lot of work and studies on our standpoint. So we actually have a Scarecrow, what we call a Scarecrow rover, which is a test rover on the Earth, which has been offloaded, off-weighted, so that it operates with a Mars level of gravity and force. And we've taken to a bunch of places out in the deserts and in dunes and things like that to be able to characterize its performance in difficult terrain. So I think we have a pretty good, and we have a Mars yard up here that you may be able to see during your stay here that basically has rocks and hills and sand and things to basically handle that. The most difficult problem, of course, is recognizing that you've got a problem before you get into the problem. And we have studied the Spirit situation, not only the last incident, but also the incident at Purgatory that occurred a few years ago. The Spirit incident and the Opportunity had the Purgatory incident, to understand exactly how we might find such occurrences ahead of time, how we might avoid them, those kinds of things. I think we have a pretty good handle on those kinds of things. We also have a pretty hair trigger with respect to our fault protection. I mean, the first sign you're in trouble is when your wheels are moving, but you're not moving, and you get high slippage events and those kinds of things. And we have developed algorithms to basically sense that and to stop. And so I think we're in pretty decent shape with respect to trafficability issues. At least we certainly have tried.
So let me add a little to that. I mean, this is why we do a program where you think about the missions you're going to fly and what they're going to do, and you grow technologically in this case, but scientifically also. the things that these guys have learned in Spirit and Opportunity have been applied, including the software I mentioned a bit ago. But, I mean, we certainly wouldn't want to run into these types of